Hello everyone and welcome to this new lecture. In this lecture, we will discuss edge linking and boundary detection. Ideally, gradient operator and LOG, that is Laplacian of Gaussian, yield pixel lying only on edges. But because of noise and other effects, intensity discontinuities are introduced. So ideally, what should happen? Gradient operators and Laplacian of Gaussian. These operators should give us only the uh, pixels which represent edges. But because of noise and other effects, uh, like the contrast and the illumination of light, because of that, the intensity discontinuities are introduced in the image. That means edges are broken in the direction of appearance. So to avoid this discontinuities in the intensity, what is done? We use edge linking. Thus, edge detection algorithms typically are followed by linking procedures to assemble edge pixels into meaningful edges. So, as I have told that, so to avoid these discontinuities in the intensity, what is done? A linking procedure is followed after these gradient or the Laplacian, so that we get a meaningful edge out of the image. So there are different approaches suggested for edge linking. So first, here we will discuss two approaches. First is local processing and the second is global processing. So in local processing, what is done is all points are similar according to a set of predefined criteria are linked, forming an edge of pixels that share those criteria. Now, if if we have got some of the pixels of the edge pixels and some other points which are similar according to a predefined criteria, then we link those pixels also to the edge. So this is how we perform local processing. So how do we perform the local processing? For that, the the two principal properties used for establishing similarity of edge pixels in this kind of analysis. So, to find the similarity between two edge pixels, what is done? Two properties are considered. Which are those two properties? The strength of the response of gradient operator used. So, what is the strength of the gradient operator used at that particular 2 points? And the direction of gradient operator. So at those 2 points, what is the direction of gradient vector? So these two properties are used for determining whether there will be a linkage between these 2 points or not. Thus, an edge pixel with coordinates x0, y0 is predefined neighbor of xy is similar in magnitude to pixel at xy if gradient of fxy minus gradient of fx0y0, this difference is less than or equal to e, where e is some non-negative threshold. So what is done? So here, suppose we have a pixel here x0 y0. It is the neighbor of xy. So it is similar in magnitude. So, so this first condition is checked by this. It is similar in magnitude to the pixel at xy if the gradient of gradient at this pixel xy and gradient at this pixel x0 y0, difference of these two gradients is less than or equal to some non-negative threshold. Then we say these two are similar in the magnitude. Same is the condition applied for the angle of the gradient at these two particular locations. So if the angle at the pixel xy and the angle at particular pixel x0 y0, if the difference between these two is less than or equal to a particular threshold, then we can say these are angle similar. These two pixels are angle similar, and this satisfies the second condition also, that is direction of gradient vector. So direction of gradient vector we find by the angle of the gradient, and the uh, gra- strength of the response of gradient operator we find by the gradient at that particular pixel values. So these two conditions are checked like this. If these two conditions are satisfied, then we say that that particular pixel which is at x0 y0 is similar to xy. So this is done in the local processing. The direction of the edge at xy is perpendicular to the direction of the gradient vector at that point. So this we have already discussed, that when we scan the image in y direction, we will get the edges which are in the perpendicular to the y direction. And when we scan the image in x direction, that means when we find the gradient in x direction, we will find the edges which are in the perpendicular to the direction of scan. So this is what is written here. The direction of edge at xy is perpendicular to the direction of the gradient vector at that point. A point in the predefined neighborhood of xy is linked to the pixel at xy if both magnitude and direction criteria are satisfied. That means a point that is x0 y0 will be linked to xy only if these two conditions are satisfied. These two conditions are satisfied, then they will be linked together. Okay, then moving forward, here one example is given. Here we have this back of one vehicle. So here the objective is to find rectangles whose sizes makes them suitable candidates for license plates. So we need to find the rectangles which have the size of the license plate, which is here, this one. So what is done, first here the gradient in y direction is found out. So when we move in this y direction, we will get the edges which are perpendicular to the y direction, so these edges will be detected. And then gradient in x direction is calculated. So when we move in the x direction, these edges which are horizontal, they will be detected, and we get this. Now here you see, we can see some intensity break in between the edges. So intensity breakage we can see, there are discontinuities in the intensity. So what is done here, the result of linking all points with simultaneous simultaneously had a gradient value greater than 25 and whose gradient direction did not differ more than 15 degrees. So these two conditions are taken. That means their gradient value was greater than 25, and their gradient directions were not differing than 15 degrees. So that means those points were linked together, and this is the output of that processing, local processing. So here we can see this box is clearly visible. Here discontinuities are removed, and the remaining edges are also clearly visible. From here we are able to remove the discontinuities up to certain level. So this is local processing. So just to recap, in local processing, we take two conditions, one for the magnitude, another for the direction of the edge. And if both the conditions are met, then we link that particular pixel to the neighboring pixel, and then like that we perform the linking, and we achieve the removal of discontinuities by doing this local processing. Then moving ahead, we have next global processing via Hough transform. So before looking at the processing for linking using Hough transform, first let us understand what is Hough transform. So let's consider a point xi, and the general equation of a straight line in slope intercept form, that is given as yi is equal to axi plus b. So suppose we have a point here. So if I want to write the equation of a straight line which is passing through this point, then this we know from geometry that it is y is equal to mx plus c. So here m is written by a and c is written by b. So in that form, if I write this, that is called slope intercept form. So in that form, if I write the equation of the straight line which is passing through this line, that will be written as yi is equal to axi plus b. Now all lines passing through xi yi satisfy the equation yi is equal to axi plus b for varying values of a and b. That means we know that from one point there are infinite number of lines which can pass. So all the lines equation can be given by this equation by having different values of a and b for different straight lines. So this can be done. So the equations of all the straight lines passing through this point can be written by this, having different values of a and b. However, writing this equation as b is equal to minus xi a plus yi, that means if I send this term in the left hand side, then I get b is equal to minus xi a plus yi, and considering the AB plane. Now here this is our xy plane, this is our xy plane, and if I consider another plane, that is the AB plane, we call it parameter plane 2. So if I consider this AB plane, then if I look at this equation, then minus xi is the slope of this straight line and yi is the intercept of this straight line. Do you agree on this or not? Yes. So this is the slope and this is the intercept. If I consider b is equal to minus xia plus yi, that means if I consider this plane a and b, this parameter plane, if I consider, then this is a this is a and this is the slope of the line and this is the intercept of the line. So suppose this is this line, this is this line, b is equal to minus xia plus yi. So corresponding to each point, we will have a straight line in the Hough transform plane or the parameter plane. Yields the equation of a single line for a fixed pair. So since xi and yi, xi and yi are fixed, so this straight line will be fixed. This is one straight line we have got in this plane. Now furthermore, a second point xj yj. So suppose this is one point xj yj also has a line in parameter space associated with it, and this line intersects the line associated with xiyi at a dash b dash, where a dash is the slope and b dash is the intercept of line containing both xiyi and xjyj in the xy plane. That means what? Here we have another point. Corresponding to this point, there will be a line in the parameter plane. So this line will be b is equal to minus xja plus yj. So this is another point xjyj. Corresponding to this line will be there. So when these two lines will cross each other in the parameter plane, and they will cross at a point, and that point will be a dash and b dash, and a dash and b dash will be the slope and intercept of this line which is joining these 2 points in the xy plane. This will be slope and intercept of this line. That means a line in xy plane is represented by a point in parameter plane, that is this point a dash b dash, and a point in xy plane is represented by a line in the parameter plane. So this is how we perform Hough transform, and we take the point into the straight line in the parameter plane. Okay, so in fact, all points contained on this line have lines in parameter space that intersect at a dash b dash. So since this a dash b dash is the that represents this straight line, so whichever points are there on this straight line, they will be represented by a dash b dash, this point in the parameter plane. That means a line in xy plane is represented by a line in xy plane is represented by a point in ab plane, that is our parameter plane. Okay, then hope this is clear. uh, Here point gives us a line, a point gives us a line, and a line gives us a point here, a point here, and this line is corresponding to this point, this line is corresponding to this point, and vice versa. The computational attractiveness of Hough transform arises from subdividing the parameter space into so-called accumulator cells. So what is done in Hough transform is these parameter x's a and b, they are divided into its expected values. That means we assume that the value of b will vary from b min to b max, and value of a will vary from a min to a max. Zero will be somewhere in the middle. Now we divide it into this matrix, and each matrix will have some value. Each matrix will have some value, and what will be that value? Let's discuss. The cell at coordinate ij with accumulator value aij corresponds to a square associated with parameter space coordinate ai and bi. Okay, so now these cells we have got, each cell will have an accumulator. Each cell will have an accumulator, and that accumulator will hold some value. And what will be that value? We will discuss. So each cell will hold a particular value, and the accumulator is denoted by aij. Now aij is a particular cell. What will be this cell? This cell is corresponding to the parameters ai and bj. I'm sorry, it should be bj here. ai and bj. So ai, suppose somewhere here ai is there, and suppose this is bj is there. So this cell is corresponding to ij, ai, bj, and the accumulator corresponding to this cell will be aij. Accumulator corresponding to this cell will be aij. Initially these cells are set to 0. That means initially the accumulator value will be 0. Then for every point xk yk in the image plane, we let the parameter a equal each of the allowed subdivision values on the x-axis, on the a-axis, and solve for the corresponding b using the equation b is equal to minus xk a plus yk. So what is done? Every point is taken from the xy plane. So suppose this point is taken. For this point, this is our equation. This is our equation in the parameter plane. Now here all the possible values of a are taken. All the possible values of a are taken. That means a min to a max. And the b is calculated, and the b is calculated. The resulting b's are then rounded off to the nearest allowed value of b. Now b cannot have any value because it is divided into fixed intervals, fixed values. So whatever value we get here, we will round it off to the nearest value of allowed b, right? So that we will take in b. Now if a choice of ap results in solution bq, then we let that apq, that is equal to apq plus 1. If suppose this is our ap, we have taken the value of ap, this one, suppose here is ap, corresponding this ap we put into this equation, and the value of b we have got is bq. So suppose bq is here, bq is here, so here is ap, here is bq. Then what is done, if it is done like this, then corresponding cell for these two values is this one. So it is represented by APQ. APQ. So its cell value will be incremented by 1. Its cell value will be incremented by 1. So this is how we calculate the value for each cell in this 2D array. At the end of this procedure, a value of q in aij corresponds to q points in xy plane lying on the line y is equal to ai x plus bi. This means what? If suppose here we have here we have this is ai, suppose this cell is aij and its value is q. Its value is q means we have q number of, and this is parameter plane and this corresponds to a point in parameter plane, so that will correspond to a line in xy plane. That will, this point will correspond to a line in xy plane, and that line will have q number of points, q number of points in the xy plane. Yes, do you agree on this? That first we calculate the value of b, and with this formula we update the values of each cell, and after that we check each cell. If suppose this is the cell and the value of this cell is q, that means the line in the xy plane represented by this point will have q number of points on that particular line. The number of subdivisions in the AB plane determines the accuracy of collinearity of these points. Now, this is the number of points will be more in the x and y direction, that will give us more precision in the collinearity of the points on the line in xy plane. Right. That is quite intuitive. As much less value we will take, that much precision we will get in the straight line in the xy plane. Now, there is a problem with this model y is equal to ax plus b. What is that problem? A problem with using the equation y is equal to ax plus b to represent a line is that the slope approaches infinity as line approaches the vertical. One way around this difficulty is to use normal representation of line, that is x cos theta plus y sin theta is equal to rho. Now as slope approaches to infinite, we cannot define this line appropriately. Yes, do you agree on this? Because this slope is what? 10x, tan theta, and tan theta, if theta approaches to 90 degree, that means a normal is there, normal to x-axis, then that will give us a infinity slope, and in that case we will not be able to represent using this equation. So what is done, this straight line is represented by this equation, x cos theta plus y sin theta is equal to rho. So we will understand first how a line is represented in this form, and then how this form can be converted into the parameter plane. So the use of this representation in constructing a table of accumulators is identical to the method discussed for slope intercept representation. So converting this equation into the parameter plane is similar to whatever procedure we have seen here. The same way we will convert this xy plane into the parameter plane. So in this case the parameter plane will be rho and theta. So here parameters are rho and theta. Here parameters were a and b. So here uh, rho and theta will vary from minimum value to maximum value. So let's understand first how we define a line by using these two parameters in xy plane. So suppose here we have this xy plane. So this is a straight line. So how will we define the straight line using rho and theta is we drop a normal from this horizon to this line. That means this angle is 90 degree. Then we measure this distance. This distance is called rho. This distance is called rho, and angle of this normal from the x-axis is theta, is called theta. So what difference will we get from the previous parameter plane? Instead of straight lines, so in the previous plane corresponding to each point we had a straight line in the parameter plane. So here instead of straight lines, however, the loci are sinusoidal curves in the rho theta plane. So here we have a parameter plane, that is rho theta plane. So in rho theta plane we will not get straight lines, we will get the sinusoidal curves in the parameter plane corresponding to each point in the xy plane. Now the range of angle theta is from minus 90 degree to plus 90 degree, since it can go like this also. So when a line is going like this, the normal will come here and the normal will form a negative angle from x-axis. So this theta varies from minus 90 degree to plus 90 degree measured with respect to x-axis. A horizontal line with theta is equal to 0 and rho being equal to positive x-intercept. So if a horizontal line is there, then its normal will be this x-axis only. So the theta will be equal to 0, and the the rho will be equal to x intercept. Wherever that line intercept with x, that will be the value of rho for the horizontal lines. Similarly for vertical lines, the theta will be 90 degree. Vertical is this way, the normal will be uh, parallel to y axis, and in that case theta will be 90 degree and rho will be equal to y intersect. And in another case the theta can be minus 90 degree if it is over here in this direction, and rho will be minus y intersect, minus y intersect. So in that way the theta will vary from minus 90 degree to plus 90 degree, and rho will vary from some negative value to some positive value, because for y intersect we get negative rho too. Okay, so this is how, this same way, the parameter plane is again divided into the uh, values of rho from rho min to rho max and theta min to theta max, where theta min is minus 90 degree, theta max is 90 degree, and rho will depend on the image dimension. And here again, corresponding to each cell there will be an accumulator that will keep a particular value, and that value will be calculated similar to we have discussed here in this slide. Now what it says next: q collinear points lying on the line x cos theta I plus y sin theta I is equal to rho I yield q sinusoidal curves that intersect at rho I theta I in the parameter plane. So if we have, suppose, q number of curves that are intersecting at a point in rho theta plane. In rho theta plane, that means there are q number of points which are lying on this straight line in the xy plane. Did you get my point? If we have x sinusoidal curves which are intersecting in the rho theta plane or the parameter plane, then there will be q number of points which are collinear on this straight line, on this straight line. Now, incrementing theta and solving for the corresponding row gives us q entries in the accumulator Aij associated with the cell determined by this. Now, again, once we get the value of xy corresponding to each point in the xy plane, we vary the value of theta, that means from theta min to theta max. For each allowable value of theta, we put here, and then we calculate the value of rho I, and that rho I, whatever value of rho I we get, that cell will be incremented by 1. So that way we calculate the value of accumulator for each cell in this. Now this is done for straight lines. This is done for straight lines. This Hough transform can be done for circles too. In that case, we need to consider here the equation of a circle, and in that case we will have a three-dimensional array, because in circle equation we will have three parameters. So the parameter space will be three-dimensional, and for each cell in three-dimensional parameter space we will have an accumulator. So one dimension will increase if we go for circle linking in the Hough transform. Now here is one example of mapping the points into the parameter plane, and then uh, finding out important results from the parameter plane. So here figure A, that is this one, shows an image with 5 labeled points. So here we have 5 points, 1, 2, 3, 4, and 5. Each of these points is mapped onto rho theta plane as shown in B. So here is point 1. So point 1 is the origin. So this is x axis, this is y axis, this is origin. So here we can see that the theta will vary from minus 90 degree to plus 90 degree, and rho will be always equal to 0, because what is rho? Rho is the distance of that point from the origin, distance of that point from the origin. So that is equal to 0 in the case if the line itself is passing from the origin. So in that case rho is 0, and theta will be the whole range from minus 90 degree to plus 90 degree. Then second we can have theta from minus 90 degree to plus 90 degree, and in this case the value of rho will range from from uh, from some negative value. So it will be some negative value in the case when it intersects. Suppose a line is going uh, in this direction. So the normal will be somewhere here, and so this direction will be a negative, and that negative value will be there, and in that case the angle will be some positive value. So that way we can have a a curve corresponding to point 2, which will have the theta value from minus 90 degree to plus 90 degree, and the rho value will change like this. Rho value will change like this, corresponding to every line which is passing through this point 2. Then corresponding to 3, here the lines can be anything from here, from here, from here. there can be many lines which can pass through 3. So here the row will range from some half of the mm, maximum row, half of the maximum row value, and again the theta will range from minus 90 degree to plus 90 degree in this case. And then this is the value for fourth, and this is the value for, this is the curve for fifth point in this plane. Now, how can we utilize this Hough transform or the parameter curve in finding out the details about these points? Now, here we see that the curve corresponding to point 1, point 3, and 5 meet at point A. These three curves meet at point A. This means what? These 3 points, these 3 points are collinear. These 3 points are collinear, and the row value for that particular straight line is 0. Row value is 0, and the angle is some minus 45 degree, because here is minus 90 degree, here will be half of that, that will be minus 45 degree. So we can see here the 1, 3, and 5 are collinear. It is passing through the origin, so the row value will be equal to 0. And since it is in this direction, so the normal will be in this direction, normal will be in this direction, and the angle with x-axis will be minus 45 degree, minus 45 degree. So that is why we, these three curves corresponding to one, corresponding to curve 1, point 1, 3, and 5, we get this point, and this shows that these three are collinear and with the angle minus 45 degree. Then another point is here, where these 3 points are uh, intersecting. So these three curves are intersecting. The point number 2 curve corresponding to point number 2, curve corresponding to point number 3, and curve corresponding to point number 4. These three are intersecting at this point. This means what? They, the these 3 points are collinear. These 3 points are collinear. The value of rho for this is half of the maximum rho, because the maximum rho has been taken is this one. Maximum rho has been taken is this one. So the half of it will be here. Half of it will be here. So if this is the straight line, if I fall a normal from this point to this straight line, it will fall here, it will be 90 degree. So this angle from x-axis will be 45 degree, that corresponds to this point over here. So this is what is shown here in this diagram. So this is how we can find out, we can find out in the parameter plane that which points are collinear in the xy plane. So figure A shows the image with five labeled points. So here 5 labeled points are there. Each of these points is mapped onto rho theta plane. So each of these points are mapped to this one. So corresponding to one, this point 1, this is the curve. Corresponding to point 2, this is the curve. Corresponding to point 3, this is the curve. 4, and this is the 5. Then the collinearity detection property of Hough transform is illustrated in figure C. So this we have already discussed, that this will give us the collinearity property of these uh, this parameter plane or Hough transform. So the point A and point B gives us that the point A, point 1, 3, and 5 are collinear, and point B gives us that the 2, 3, and 4 points are collinear, and the points A and B gives us the rho and theta values also. Then figure D indicates that the fact that the Hough transform exhibits a reflective adjacency relationship at the right and left edges of the parameter. That means the this point and this point correspond to a adjacency in the uh, in the point in the xy plane. So here the 2 and 5 are meeting at a point, so these two are adjacent to each other. So that way this shows us the adjacency of these points. Now, how can we utilize this Hough transform by for image linking or edge linking? So edge linking can be performed using Hough transform as. So what is done? First, compute the gradient of an image and threshold it by obtaining it to obtain a binary image. That means first we need to compute the gradient of the image. That means we need to apply privets or Sobel's filter over it. So we calculate the gradient of the image, and then we threshold it and we get the binary image. Then specify subdivisions of row theta plane. So now after doing this, we specify the subdivisions of theta and rho in the parameter plane. Examine the counts of accumulator cells for high pixel concentration. Now, for each point in this parameter plane, we calculate the value of accumulator by using this method. So this we have already discussed, that how do we calculate the accumulator value for each cell. Then after that, examine the relationship between the pixels by choosing pixels in a chosen cells. So we choose a particular cells of the parameter plane, and from those chosen cells, we define that these pixels are collinear and they have strong response in the image. So this is how we can use this Hough transform in the linking of edges. So this is one example given here. This figure A shows an aerial infrared image containing two hangars and a runway. So these two are hangars, and this is one runway over in this image. So in this, first what is done? A Sobel operator is applied on the image, and that is thresholded, and we got the thresholded binary image in the figure B. So figure B is thresholded gradient image obtained using the Sobel operators. Then C shows the Hough transform of the gradient image. So this image Hough transform is calculated. So this is the Hough transform. So here we see that the locus of each point in the Hough transform is sinusoidal. Here everything is sinusoidal. Now we got the image B, sorry, image D. How did we get this? Figure D shows in white the set of pixels linked according to the criteria. So how did we link the pixels? They belong to one of the three accumulator cells with the highest count. So those pixels are linked whose accumulator cells had the highest count in the Hough transform parameter plane, and no gaps were longer than 5 pixels. If two pixels are more than 5 pixels apart, then they were not linked. So these two conditions were taken, and we have got this as the output. Note the appearance of the gaps as a result of linking. So here these edges had the discontinuities in the intensity. Here also discontinuities were there. So that is not visible here. We have linked all the intensity discontinuities in the output of image linking. So that's it for this lecture. This is how we perform edge linking in the local and in the global. Right? So that's it for this lecture. We will meet in the next lecture. Thank you.